5, 4, 3, 2, 1. I'm going to do a few problems here that are mostly objects that are in equilibrium, which means they're not accelerating. I think we do have an acceleration as the last problem on here. It's actually a conceptual question. But we'll give these things a shot, and most of them I'll be able to have a choice of working them either using vectors and components, or if we only have three forces acting, we can treat them as a three-vector problem, and I'll show you how we can do that. We'll start off with this one. A young girl convinces her grandfather to sit in a swing at a park. When his legs are off the ground, she pushes as hard as she can on his back and manages to move him slightly so that the chains supporting the swing make a 12.5 degree angle with the vertical. She holds him there for a while before giving up and going to get on her own swing. What force was she exerting on him while he was motionless? Assume the grandfather and the swing on which he is sitting act as a single object with a combined weight of 190 pounds, and you can stay with pounds all the way through since it is a unit of force. All right, well, let's kind of start off with a sketch here. We'll imagine that this is one of those big swings at a park. Here's the vertical direction. Let's see. Coming down here is the chain that the guy is sitting on, and I have no idea how to draw this. Anyway, he's got his hands on there and his feet are sticking out, and down there on the ground is granddaughter pushing on him. So that's the situation anyway, and this is the 12.5 degree angle. So let's do a free body diagram for the grandfather and the swing. Here's what we have. We'll have mg, the weight of grandfather and the swing. That's the 190 pounds. And then over here is the force of the granddaughter. She's pushing in that direction, and they're attached by a chain to the top of the swing, and that's going to be up here in a direction of 12.5 degrees. And for a little while, at least until the granddaughter runs off, they're in equilibrium and just sitting there. So let's call that the tension, and we'll just make it like that. Now, Newton's second law in vector form is always just the sum of the forces is equal to ma, and again, that is just the generic version of Newton's second law. For this particular problem, there's no acceleration, and we just have these three forces, so we can say that the force of the girl plus the weight of the grandfather and the swing plus the tension equals 0. Now, we could come up with a coordinate system. In fact, I'll set it up very quickly here. I'll just let x point in that way and y point in that direction. In this coordinate system, mg would be minus mg in the j-hat direction. The force of the girl is going to be minus whatever the force the girl exerts, that's in the i-hat direction. And then we'd have the tension, which is going to have two positive components. Tension, let's see, will be whatever the magnitude of the tension is times the sine of 12.5 degrees. See if you can figure that out and make sure that you agree with me on that. That's in the i-hat direction, plus the magnitude of the tension times the cosine of 12.5 degrees in the j-hat direction. And the reason that we're using the sine for the i-hat component and the cosine for the j-hat component is because the angle is measured off of the y-axis. when we get that v naught x equaling v naught cosine of theta, that's because we're measuring the angle up from the x direction. So that's what we've got here. Now, if all we're after is the force that the girl exerts, let's see. Well, we need to figure out T first, I guess, going about it this way. If we just look at the j-hat terms, we would have T cosine of 12.5 degrees. This is the sum of the forces in the y direction, minus mg, that's right, mg is equal to 0, so the tension is going to be mg over the cosine of 12.5 degrees. And then, if we look at the sum of the forces in the x direction, we will have, let's see, the tension times the sine of 12.5 minus the force of the girl that the girl exerts, and those will equal 0. So the force the girl exerts will equal T sine of 12.5 degrees, but we figured out that T is equal to mg over the cosine of 12.5 degrees, and we get Fg is equal to mg over cosine of 12.5 degrees times the sine of 12.5 degrees, and that is equal to mg over mg times the tangent of 12.5 degrees. Excuse me. Okay, so we could plug in the numbers and figure that out. Now, let's do this as a 3-vector problem, and this is just a matter of drawing these things. So we've got Fg plus mg plus t is equal to 0. That means when you add these things together vectorially, they'll come back to where they started. So here's what we have. I'll just draw the picture here. The force of the girl is sideways to the left, or the force that the girl exerts. mg is straight down, and we start that from the front end of F sub g. So here's mg, and then we add to mg the tension, and we have to go right back to where we started. Now, this is not at all correct angle-wise, but that's okay. We get back to 0. Here's the tension. And the tension made a 12.5 degree angle with the vertical. Okay. Well, let's see. The tangent of 12.5 is equal to F sub g over mg. So or the force that the girl exerts is mg times the tangent of 12.5 degrees. And we get the same thing that we did down here, but for a lot less work. And that when you have a 3-vector problem, they're very nice to solve that way. And we could plug in the numbers here. Actually, I'm kind of curious. I did sort of work this out ahead of time to see if it was reasonable. mg is 190 pounds, so 190 tangent of 12.5. Okay, it's about 42 pounds, something like that. And that's a reasonable force for a small granddaughter to be able to exert. So there's our first one. We solved it with the 3-vector method. Okay, another one. A bicyclist coasts down a steep hill with a slope of 8.53 degrees. Now, that may not sound steep, but it's actually a 15% grade, which is steep if you ever have to walk up one, or if you ever get to ride down one on your bike. It's kind of fun. Anyway, slope of 8.53 degrees at a constant speed of 22.3 meters per second. The cyclist and his bicycle have a mass of 91.8 kilograms. The reason the cyclist is moving at constant speed is because the air resistance is so large and is in a direction opposite the velocity of the cyclist. What is the magnitude of the force of the air resistance in this situation? Air resistance is kind of an interesting thing. Sometimes it's proportional to the velocity, so that the faster you go, the greater the air resistance comes. Sometimes it's proportional to the square of the velocity, or the square of the speed, and that gets tougher real fast. So anyway, let's make a sketch here. I don't know, we've just got this 8.53 degree slope, and a bicycle here. Let's see. Whoops, forgot that's supposed to go down there. Oh well, we got a bicycle, and there's a person sitting on it with their hands on the handlebars. Okay, so there's our sketch. Now, a free body diagram here. Let's figure out what we've got acting force-wise. We would have mg. Okay, we'd have a normal force in this case, which is perpendicular to the road. Normal means perpendicular, and so there's that. And then there's the resistive force of the air going back up the hill here. So I'll just call that F sub r for a resistive force. And that's it. Okay, so Newton's second law, the sum of the forces equals ma, becomes, we can add them in any order we like, I guess, n plus F sub r plus mg. Now, it says bicyclist coast down a steep hill at a constant speed. Okay, turns out the speed doesn't even matter. So, we get 0 for that thing. And we can draw any kind of a picture we want on this thing, but the first two forces are at right angles to each other. So if I draw them, I would have n going up here like this. F sub r is at a right angle to that, goes up like that, and I have to reach a point where when I come down from F sub r, I get right back to where I started with a vertical line. So here's mg. Now, somehow we have to get an angle in here that's going to work pretty well. Actually, this thing makes the 8.53 degree angle, and that would be what's up here. Okay, because you could come back here and draw another 8.53 degree angle. I think those are alternate interior angles or some such thing. So this would be 90 minus 8.53, which is going to be 91 point whatever it is. But this one down here, no, not 91, 81.47, I think. But this one down here is 8.53 degrees. And monkey around with that to convince yourself. Okay, or you could think that the normal force is going to make some kind of an angle with the horizontal, but that should be right. So how do we figure this out? We want to know the magnitude of the force of the air resistance in this situation. Well, if I look at this triangle here, F sub r is the side opposite that 8.53 degree angle, and F sub r divided by mg is going to be the sine of that. So F sub r over mg will equal the sine of 8.53 degrees. F sub r is just going to be mg times the sine of that thing. And what do we have? The mass is 91.8 kilograms, bicyclist and bicycle. So fairly simple problem. Hmm, 91.8 and 9.81 have the same digits. I don't know if I did that on purpose or not. Okay, I get about 134 newtons for that. By the way, that speed is, you can convert meters per second into miles per hour. It's a smidgen over 50 miles an hour, I think. About 50.2 miles per hour. What I got when I did that, or actually to approximately a little bit over 50 miles an hour. So that's a pretty good speed. So another 3-vector problem, and if you're lucky enough to get one, sometimes you'll have only 2 forces acting and you'll have acceleration. Sometimes you'll have equilibrium and 3 forces acting, so then you can use that as a 3-vector problem. I think I skipped one of the problems. It was on the back of the grandfather thing. Oh, here we go. Yeah. This is getting into an electric field force, although we're just interested in the force that the electric field exerts. We have a charged sphere of mass 2.85 times 10 to the minus 4th kilograms, not very big, suspended from a very lightweight string. An electric force acts horizontally on the sphere so that the string makes an angle of 37.2 degrees with the vertical when at rest. Find the magnitude of the electric force and the tension in the string. Turns out the geometry of this situation is just like the grandfather on the swing. So here's what we have. The angle's bigger, but got a suspension point. We have a string that's tied to this little charged sphere, and it makes an angle of 37.2 degrees. And this is our little charged sphere here. Well, let's do a free body diagram here. Okay, forces that are acting. One of the forces is going to be this sphere has mass, so it'll be the weight of it, mg. That's always the low-hanging fruit, mg. There's an electric force acting horizontally sideways, so F sub E, the force of the electric field. When we get to electricity spring quarter, we'll find out that this force here would equal the amount of charge on the sphere times the electric field. And electric field is another vector. Okay, don't worry about that. That's for the future, but just thought I'd point that out. Okay, and then we've got the tension in the string. So something like that. All right, sum of the forces. equals MA, but in this case A is 0, so the sum of the forces are 0, and we'll just have F sub E plus mg plus the tension are equal to 0. Now, you might want to pause this and see if you can draw the force triangle that I'm going to come up with. Go ahead and do it on yourself. Remember, or do it yourself. So pause the recording and see what happens. Okay, I'll go ahead and draw that. F sub E is horizontal to the left, so there's F sub E. Mg is straight down. And I'm not worried about scale or anything like that. I just happen to know this thing makes that 37.2 degree angle with the vertical. And this is also 37.2 degrees. Alternate interior angles, I think. And so there's the tension. Okay, and here is 37.2 degrees. Now the first thing asks for the magnitude of the electric force. Well, the only thing I know in here is the mass of this thing, and so I can calculate its weight. But F sub E divided by mg is the side opposite divided by the side adjacent. That's the tangent. So F sub E over mg is equal to the tangent of 37.2 degrees, or F sub E is equal to mg tangent of 37.2 degrees. Tossing in the numbers, 2.85 times 10 to the minus 4th kilograms. That might be about the mass of a single coffee bean. I'm not sure. Probably actually less than that. But times that tangent. So F sub E is not a very big number. Oops, clear. Oh, somehow I got way out of whack on this thing. Okay, I get about 2.12 times 10 to the minus 3rd newtons. So, not much. Okay, but that's a reasonable thing. Actually, if we were looking at a single electron and considering a force on it, we'd end up with numbers much smaller than this when you're looking at things like that. Okay, the second thing asks the magnitude or the tension in the string. Well, now that I know F sub E, I could look at this, and F sub E is the side opposite, T is the hypotenuse of that triangle, so F sub E over T is going to be the opposite over hypotenuse is the sine of 37.2 degrees. Okay, be careful when you do this. I can do this in my head, and I know that the tension is going to equal F sub E divided by the sine of 32. But if you have a tendency to make a mistake when you do that, start by multiplying out from underneath by T. So F sub E is going to be T sine of 37.2 degrees. Notice I've just been dealing with the magnitudes of these forces once I get the force triangle drawn. And T, F sub E divided by sine of 37.2 degrees will equal T. So you could just take this number and divide by the sine of 37.2 and you'd have the tension. So another 3 vector problem. Okay, let's see. Bicyclist, here's the last one. It's more of a conceptual thing, but a ball is hanging from a long string that is tied to the ceiling of a train car that is traveling eastward on horizontal tracks and speeding up. An observer standing in the car sees the ball hanging motionless with respect to her. She's standing in the car, she's looking at this ball, and it's motionless with respect to her. Well, if she's in that train car and it is traveling east and speeding up, she is accelerating and the ball is also accelerating. So, draw a clearly labeled free body diagram for the ball. Is the net force on the ball 0? Well, think about this. If the ball is at rest with respect to the train car and the train car is accelerating, the ball must also be accelerating. Okay, well, this is a train car that the side of it just consists of a giant window. And this person is looking up at here at this ball that's hanging from a string, but this has an acceleration in that direction, so must the ball. What force can produce that acceleration? Well, a vertical string won't do it. Okay, a vertical string can only exert an upward force. The string has to be making an angle so that the tension, if you do a free body diagram for the ball, it has a downward force mg. It's got to have a force at an angle like this. The component of this tension that's up will equal mg. The component of the tension that's to the right is going to be the force that's accelerating that ball. So this person will see the ball hanging at an angle there. Okay, that was a few 3 vector problems, objects in equilibrium. There's all kinds of 3 vector problems. You can have things like if you've got a beam here and 2 cords that are attached to some ball here, some object that has a mass of m. If you do a free body diagram, and maybe this one is the angle phi with the horizontal, and this one is the angle theta with the horizontal, then you can make a free body diagram that'll have mg downward, whatever the mass of the thing happens to be, the tension in this direction. This angle here will also be phi, so this will make an angle phi, and I would call this T sub r for the tension on the right. And then there's also a tension on the left that makes an angle of theta up there, so this would also be theta, and I would call this force T sub L for the tension acting to the left. And if your angles are nice enough, you can do a 3 vector problem. Sometimes that's not so nice. If these things aren't 90 degrees, it may be better to figure out components. Otherwise, you're going to have to use the law of cosines to try to figure out what's going on with that. But you might be able to do it. Anyway, actually the angle between the vectors would be 180 minus the quantity phi plus theta. So you could probably do something with that. Okay, we'll stop here, and objects in equilibrium is what you just saw.